Hey, more fun with circles. Today we're going to be taking a look at inscribed angles and inscribed polygons. Notice that the angle is not a central angle, right? The vertex of the angle is not at the center of the circle. Instead, the vertex of the angle is actually on the circle. So the inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. And then the arc that lies between those two lines, or rays, or segments, is called an intercepted arc. Because remember, when we define that angle, we would also define it as the endpoints of rays have a common point. Right? So we have a ray that starts at Q and then goes through R forever, and a ray that starts at Q and then goes through P forever. Or we could actually extend those as lines forever in both directions. Right? Now, of course, when we talk about the chords, we're only talking about the line segments contained within the circle. But of course, those segments can be extended into rays or lines, as the case may be. So that intercepted arc, in this case, goes between point P and point R. Now, big difference. All right, is going to be how this measurement's going. Notice we can put a little chord in there. So angle B intercepts arc AC. Angle AC subtends angle B. Segment AC subtends angle B. Right, again, when we defined angles, we talked about rays. But of course, when we're talking about just the part of that ray that's inside the circle, it's a line segment, right? It's a chord. And subtend is just kind of a fancy way of saying, hey, it goes with that angle. So instead of saying, hey, arc AC goes with angle B, we say, oh, arc AC subtends angle B. Or instead of saying, hey, that segment AC, then you see that line segment, that chord AC, say, hey, it goes with angle B, we say, no, it subtends angle B. Right? Just a fancy word so we know which angle to associate it with. Well, truth be told, if you take a look at the picture, it's pretty self-evident. Okay, so now let's get to the measurement. This is where it's really different from before. Right? Because before, it was a central angle, where the vertex was at the center of the circle. But this time, because the vertex is on the circle, notice that the measurement of the arc is not the same as the measurement of the angle. Right? The measurement of the angle is only half of the measurement of the arc. Right? So central angle, measurement of the angle was equal to the measurement of the arc. But inscribed angle, where the angle is actually on the circle, the measure of the angle is only half the angle of the arc, the measure of the arc. Getting tongue-tied again. Okay, so let's take a look at a picture. Let's get some numbers on here. We want the measure of angle T. Well, I see arc RS measures 48 degrees. I know the measurement of angle T has to be half of that measurement. So the measure of angle T has to be half of 48 degrees, which is 24 degrees. How about the measurement of segment QR? I'm sorry, the measurement of arc QR. Nothing but tongue-tied today. Holy cow. Well, I've got no clue how to figure out the measurement of arc QR, but I could do the measurement of arc TQ, right? Because arc TQ subtends that 50-degree angle. I know that arc has to be twice that angle when we talk about the measurements. So 2 times 50 degrees is 100 degrees. Now, how is that going to help me find the measure of arc QR? Because that's really what I'm after, right? I just want the arc QR, not the arc TQ. Oh, we have a diameter, don't we? Segment RT, because it goes through the center of the circle, it is a diameter. Therefore, we're looking at a semicircle, right? Arc TQR is half of a circle, so it has to add up to 180 degrees. So the piece we don't really want that measures 100 degrees will actually help me find the piece that I do want. Because 180 degrees is semicircle, subtract 100 degrees, that's the measure of arc TQ, leaves us with just 80 degrees, which is the measure of the arc we do want, the measure of arc QR. Ooh, a lot going on with this picture. Let's find the measurement of arc RS. Well, it looks like it subtends angle U. So I know the measurement of the arc has to be twice the measurement of the angle because it's an inscribed angle. So if I double 31 degrees, I get 62 degrees. Measure of angle STR. Now, how am I going to do that? I don't know the measurement of angle T. I mean, if I knew that measurement of angle T, then I could probably do something. Wait a minute. The measure of angle STR, it's half of the measurement of arc RS. And we just figured out the measurement of arc RS. So those are congruent angles. Right? Angle U and angle T are both 31 degrees. Because arc RS subtends each of those inscribed angles. Right? They're congruent. Angle STR has to be congruent to angle RUS. Of course, notice I can also just call them angle T and angle U because there is no other angle there. Right, so I can choose to use all three letters or choose just one letter. So that brings us to this theorem that those inscribed angles are going to have to be congruent because the same arc subtends each of them. All right, arc AB subtends angle D, arc AB subtends angle C. So angle D and angle C have to be congruent. All right, angle ADB has to be congruent to angle ACB. And we basically just proved that at the previous example. So let's do a few practice questions here. Let's see if any of this is sinking in, if we're understanding any of it. Number 1. What is the measurement of that good old angle G? Right? Well, I know it's got to be half of that arc. Again, you notice that equation editor is giving me fits with the arc symbol on that FH. It's got to be half of 90 degrees. It's 45 degrees. Find the measure of arc TV. Well, this time I'm going to have to multiply by 2. Right? If the angle is half of the arc, then the arc is twice the angle. Twice 38 is 76. So the measure of arc TV has to be 76 degrees. Okay, let's find an angle this time. Okay, at first glance I'm thinking, how am I going to figure this out? But I know that those angles have to have equal measurement because the same arc subtends each of them, right? Arc ZW subtends each of them. So I know each of those angles has to be 72 degrees in measurement. Okay, more vocabulary. I guess we can't just simply say that the polygon is inside the circle. We got a fancy word saying inscribed. Can't just say the circle is on the outside. We have to have a special word, circumscribed. Now, the one thing we got to point out, though, is not only is the polygon inside the circle, but each vertex of the polygon is on the circle. All right, so if it's a 5-sided shape, it's got to touch the circle 5 times. If it's a 3-sided shape, a triangle, it'd have to touch the circle 3 times. All right, if it was an octagon, it'd have to touch the circle 8 times, right? Every vertex of the polygon must touch the circle. Notice we're not calling them tangent, right? Because if we extended those lines, they would intersect the circle, not be tangent to it, right? Each side of that polygon intersects the circle twice, so, right? So even though we say, hey, it's just barely touching, we're not talking about tangent here. Right, because each of those sides of the polygon are chords. Now, of all the polygons we could possibly inscribe, one of the most interesting is not only a triangle, but a right triangle. Especially a right triangle that happens to have one of the sides as a diameter. If we have a right triangle, the hypotenuse is a diameter. Right? If angle B is 90 degrees, we know the arc that subtends it has to be double. Well, double 90 degrees is 180 degrees. That's half a circle, semicircle. So the hypotenuse has to be a diameter. Now again, notice they're mixing things up here. They're not using C as the right angle. They're using B as the right angle. And we go back and forth. If I know it's a right triangle, I know it's a diameter. Or if I know it's a diameter, then I know it's a right triangle. All right, so if it's 90 degrees, I get a diameter. If I know it's a diameter, I know it's 90 degrees. All right, it goes both ways. If the measure of angle ABC is 90 degrees, AC is a diameter. If AC is a diameter, measure of that angle is 90. If I know one, I know both. Quadrilaterals are four-sided friends. If it is inscribed, I know the opposite angles are supplementary. In other words, the opposite angles have to add up to 180. Because opposite angles subtend the entire circle. Right? If I'm looking at, like, for example, angle E and angle G, part of the circle subtends angle E, the other part of the circle subtends angle G, so they subtend the entire circle. So half of 360 is 180. They gotta be supplementary. All right, so measure of angle D plus measure of angle F has to be 180 degrees. Measure of angle E plus measure of angle G also has to add up to 180 degrees. Both pairs have to be supplementary pairs. Well, is it possible to figure out the value of x when I don't see anything really labeled here besides that angle is 2x? Well, yeah. AB is a diameter. Right? Segment AB is a diameter. That chord is a diameter. I know angle C has to be a right angle. So the measurement has to be 90 degrees. 2x has to be 90, so x has to be 45. Well, since I got a quadrilateral, opposite angles have to be supplementary. So if angle D and angle F, if their measurements have to add up to 180, I know Z plus 80 has to be 180. Z is 100. Measure of angle E, measure angle G. They've got to add up to 180. So if I've used up 120 degrees on angle E, 60 degrees is left over for angle G, so Y has to be 60. We've got a worksheet, and then IXL, angles and inscribed right triangles. So we'll be playing around with right triangles.